Okay, in this video, we're going to continue with the example of chapter 3. So we move to example number 3 here. And example number 3 focus more on the equivalent circuit of the induction motor. Okay, so in this example, we have the parameter of the induction motor, which is 460 volt for three-phase input voltage with 25 horsepower and 60 hertz, 4 poles, and Y connected also. So here we have the list of the parameter for the equivalent circuit of the induction motor. So as we learned before, how to represent the induction motor by using equivalent circuit, we see and we said the equivalent circuit of the motor or of the induction motor is somehow similar to the induction to the equivalent circuit of the transformer, because both of them they work on the induced voltage principle. So but the induction motor is rotating, the transformer no rotation. Okay, so the representation of the in the equivalent circuit of the induction motor, we have the resistor for the stator, the reactance for the stator, and also we have the resistor of the core, the magnetization reactance. We have the resistance for the resistance of the rotor windings, and also we have the representation for the different losses of the induction motors. So as you can see here, the value of the resistor windings of the stator is 0.641, and the stator or the rotor windings resistance is 0.332. So we have R1, R2. We have X1, which is the reactance of the stator winding, which is 1.1, and the reactance of the rotor winding is 0.464, and also the magnetization or reactance is 26.3. Okay, it said the total rotational losses here, which is the total rotational loss means all the mechanical losses, which is 1100 watt, and are assumed to be constant, so it's not change with the times. I mean with the rotation, the load, so it's constant for all load. The core losses is lumped with the rotational losses, so the value of RC here is omitted, so we cannot see RC here because it represents the core loss. So it's omitted or is actually included in the value of the rotational loss here with the rotational losses. For the rotor here, a slip, which is the value of S here, I said S is equal to the value of S is equal to point oh to 2, because this value over as a percent, so we divide over 100. Okay, the rated voltage and rated frequency, find this the value of slip at the rated voltage and rated frequency. Actually the rated voltage is here is for 60 volt, rated frequency is here is 60 hertz. Okay, so these are the requirement we need to find, which is the speed of the motor. When we say the speed here is the machine speed, and stator current, power factor, P converted and P out, tau induced and tau load, which is the torque, the induced torque and the load torque. Then at the end, we need to find the efficiency. Actually, these are very important parameters for the induction motor, and we need to learn how to find all these parameters based on the given values for the equivalent circuit of the induction motor. Actually, we can see here, this is the equivalent or the approximate equivalent circuit of the induction motor, and we already see in chapter 3 how to simplify the induction motor equivalent circuit. It was consist of R1, X1, RC, XM, and X2 and R2 over S. Then how we split the value of R2 over S, this value of R2 over S, which is the resistor of the rotor, when we consider the frequency in the rotor is not the same as the frequency of the stator, so the value of R2 here divided by S, so it is consists of R2 plus R2 times 1 minus S over S. So this is the value of R2. This the two resistor represent the value of R2 over S, and we have here X2, which is the reactance of the rotor. We have XM here, the magnetization reactance. R core here or RC is omitted because in the question already said The core losses are lumped with the rotational loss, so no RC here, but we still have R1 and X1. Okay, so if we want to find the speed of the motor here, the first part, which is the speed, you just need to use the formula of the speed, which is Nm. You can see here Nm equal to 1 minus S times Ns. Okay, so we have S already 0.22, so we can Ns, we can calculate Ns, which equal to Ns equal to 120 F over P, which is uh, here 120 times 60 hertz over P, which is the number of pole here is 4 poles, so it is 4. Okay, so the Ns here is equal to 1800 rpm, or revolution per minute. So this is the first part of the question, which is the speed. This is Ns. Nm, which is the required here, is the speed of the machine, equal to 1 minus 0.022 times 1800, which is the value of Ns. So it will give you 1760 rpm, or revolution per minute. Okay, so this is the speed of the motor. The second is the stator current. When we say stator current, we are talking about the value of I1 or IL, like we learned before how to find the input current to the stator winding, which is the current flow from the mains to the stator windings of the induction motor. So in order to find the value of I1 here, we need to find the I1 in our circuit. You can see here the value, or the I1 value here, or the I1 current is placed is here. So this is the current which go through the I1. It's the same. It's go through stator windings. It's divided into magnetization current, and then also divided to the rotor current. So the value of I1 here, if I want to find the I1 by using the formula of Ohm's law, which is I equal to V over Z. Okay, it's Z here is represent is the impedance, but previously we say V over R. If there is no reactance, it will be over R, but if there is reactance, it will be V over Z, and Z here equal to R plus JX. Okay, it consists of the resistance and the reactance. Okay, so in order to find the current here, I1, current I1 will equal to the voltage V1, which is the V phase here, or the phase voltage of the induction motor, over the total impedance of our circuit. So I need to divide this one over the total impedance, which include R1, X1, R2, and R2 over S. Okay, this also we call it R2 over S. These two value R2 over S plus X2 and also Xm. So this impedance, we call it the input impedance, which is Zn. So Zn here is equal to R1 plus Jx1, which is this one, plus Zf. Zf represent the whole impedances on that side. Okay, so it's include the value of Xm in parallel with the value of the router reactance and router resistance. Okay, so the value of ZF here, you can see from the formula, ZF is equal to RF plus JXF, these names, so it can be split into resistor and reactance, which equal to R2 over S. This is the R2 over S value, which is represent R2 times 1 minus S over S plus R2. So this the whole, we call it R2 over S, plus Jx2. So this is Jx2 here. This is Jx2, which is represent the reactance of the router in parallel. So this is the whole circuit here, or the whole router circuit is connected in parallel with the Xm value. So this is the Xm value actually. So here we have the Xm. Okay. So all this circuit, I mean in the router circuit in parallel with Xm, this will give you the value of Zm. If we can calculate the value of ZF, we can easily find the value of Zn, because Zn here will equal to R1 plus X1 plus ZF. We already have R1, in the question here, he gave you the value of R1, he gave the value of X1. Okay, so our task here will be the first we need to calculate the value of ZF. After we find ZF, we need to find the value of Z input. After we find the value of Z input, we can find the value of the current, which is V over Z input. Okay. So how we can calculate the value here of Z2? So the value of Z2 here represent the reactant, the impedance of the router winding, of the router bar. So the impedance of the router bar, this is the router bar from this point A, B on that to the right. The router bar consists of reactance, which is X2, and resistance, which is R2 over S. So the value of Z2 here, Z2 will equal to the value of R2 over S, which is here, R2 over S represent this value plus that value, so it give you R2 over S plus JX2. So this is JX2 here, this is X2. Okay, so this will give you the value of Z2. So R2 is given in our question here. He gave you R2 equal to 0.332 and X2 also is given, which is equal to 0.46. Okay, so we just need to substitute for the value of R2 and the value of X2. Okay, so the value of R2 is equal to 0.332 over S. What is the value of S here? The value of S is equal to 0.022. 0.022 plus J x2. X2 is equal to 0.46. 0.464. Okay. So this will be the value of Z2 here. It's in rectangular form. You can calculate the total. That means you add you calculate this value, and it will give you the total or the rectangular form, which is 15.09 plus J of 0.464. Okay, so this is a rectangular form. You use your calculator to convert it into the polar form, which is 15.1 with the angle of 1.76. This you just use your calculator to convert from rectangular form to polar form. Okay, so this is the value of Z2. I found the value of Z2, which represent this area. Now this represents Z2 is in parallel with XM. Okay, so in order to find, and both of them, when this Z2 in parallel with XM represent what? Represent ZF, which is R2 over S plus JX2 in parallel with JXM. So this is will be ZF. I have already Z2. Now I calculate the equivalent of ZF, which equal to Z2 in parallel with XM. So ZF here, 1 over, when you calculate the parallel pole or the parallel resistors, we said 1 over R equivalent equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Same for the impedance. 1 over Z equivalent equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3 and so on. So 1 over ZF here equal to 1 over JXM plus 1 over Z2, since they are in parallel here. So it will be 1 over ZF equal to 1 over JXM plus 1 over Z2. So this will give you ZF. If you want ZF, it will equal to 1 over JXM plus 1 over Z2. You just need to substitute for the value of XM, which equal to, in the given here, it's XM is equal to 26.3, and the value of Z2, which you already calculate here, is 15.1. Okay, so you substitute for these values in order to find the value of ZF. After you find the value of ZF here, so you can see here in the slide. So This is the value of ZF equal to 1 over Jxm plus 1 over Z of Z2. We substitute for the value of Jxm. The j in the denominator here has become negative j in the numerator, so it's become negative j 0.038 plus this. We substitute the value, we divide it over z2, 1 over 15.1, 1 over 15.1, it gives you this value. With this angle is 1.76. When it's convert from denominator to numerator, it's become negative here. So the total will be equal to 12.49 with the angle of 31. Okay, so this is the value of ZF. But we don't want only ZF, we want to find the value of Z1 or the input impedance. Okay, so ZF here, or the input impedance of our circuit, will equal to, you can see here, now until now we find until this point ZF. ZF represent XM in parallel with XM, in parallel with Z2. Then we need to find the value of Z1. So Z1 already given R1 and X1 plus ZF. It will give you the total Z impedance, which is R1 plus JXM plus ZF. So we substitute the value of ZF, the value of X1, the value of R1. R1 and X1 are given, so we can easily find the value of ZF or Z total. So the Z total here, or Z1 or the Z total or Z input, is equal to the stator Z, or the Z1 plus the ZF. ZF already calculated, and Z stator already given by 0.641 plus J1.06. You can see here 0.641 plus J1.016. This is the stator impedance, the stator reactance. So the value of the Z total here represent the sum. You just add them in rectangular form, then you convert them into polar form. So in the polar form, you have, this is the magnitude of the input impedance, which is Zn, or Z total here, which is the same, but we mean it the input impedance, and this is the angle of the input impedance. Why we have angle? Because usually Z consists of R plus minus JX. Okay, so it depends on the value of X here. We should have, when we convert it into the magnitude, so it will be R square plus X square. So it will be magnitude of Z with the angle of Z. Angle of Z is tangent of X over R. Okay. Then now, after we got the value of Z total here, we can find the value of the input current, which is the question number 2, stator current. Stator current, which is I1 here, we said I1 will equal to the voltage V1 over Z input, or the input impedance, or Z total, which is the total impedance of your induction motor. Okay. So we can see here I1 equal to V phase over Z. Why V phase? Because the current will go for each phase. We are not going to talk about the 3-phase here, which is 460. We need to convert the 460, or the voltage of 3-phase, into a single phase. So V phase means 460, which is for 3-phase, divided by Z3. V phase equal to V line over Z3. V line equal to Z3 V phase. Okay, so since we have here, we are focused about B phase, so we need to divide the given voltage, which is 460, with the angle of 0 actually for the voltage, over Z3, divided by Z total, or Z input here, which is 14.07, with the angle of 33. So this will be the value of the input current, or the stator current. It's 18, the magnitude is 18.8, and the angle is negative 33.6. From this angle, we can find the third part, which is the power factor. So the power factor actually represents the cosine angle of the current here. So the current angle is 33.6. So cosine, or cos 33.6, will give you the value of 0.833, and it is lagging because we are talking about, we have here negative, and also we are talking about the inductor. no capacitor. So we are talking about in the machine here, we are talking about inductor. So always the power factor of the induction motor will be lagging. So the power factor is 0.833 lagging. Okay. So this is the third part, or the third requirement of this questionnaire. The fourth one is be converted and be out. Be converted and be out. And when we talk about the be converted and be out here, we need to focus more on the power flow graph. The power flow graph, in the power flow graph, we know that the B in will divide it into two main parts. It will be one go for feeding the stator and core losses. The other one will be converted power, which go to the rotor circuit. Okay. So here the question said, find the B converted and B out. So in order to find the B converted and B out, we have the input power here. We can calculate the input power from the given current, the given voltage, and the calculated current. So we have the given voltage is 460, and the formula, as we said before in the power flow graph, it's CH3 VLIL cosine theta. Okay. So since it is set 3 VLIL cosine theta, we have set 3 here. This is the VL, means the line voltage, which is the three-phase voltage. This is the line or the phase current, which is 18.8, and this will be the power factor which we calculated here. Okay. So it will give you the input power, which is 12.53 kilowatt. Okay, or 12,530 watt. Now we need to find the value of the stator losses. Then the value of the air gap will be P in minus the stator losses. So what is the value of the stator losses here? So as we can see here, the voltage, which, or the input voltage here, will go through, as we mentioned before, we start from the input voltage, which is Bn equal to set 3 Vt IL cosine theta. We substitute for Vt IL cosine theta, we find the value of Pn. Then if we want to find, based on the question here, we need to find B converted and B out. So we need to calculate, or we need to find these values. B converted, which is here. This is the B converted, and this will be the P out. So we need to find these two values. So in order to reach to this point, we need to find what is the B stator copper loss and what is the core loss. Then we can find the B air gap. From B air gap, we deduct the value of rotor copper loss. We can find the B converted. From the B converted, we deduct the value of mechanical losses here. We got the value of P out. Okay. So from, you can see here, the stator copper loss is equal to 3I1 square R1. Why I1 square? Why 3? Because we are talking about three phase. Okay. Since we are talking about three phase here, so this we are talking about three phase, so we have 3 here. 3I1 square R1. What is R1? R1 is given in our question. What is I1? I1 is the one that we calculated here, which is equal to 18.88. Okay, so we just substitute. Since we are talking about the magnitude, so we just take the magnitude value. So it's 3 times 18.88 all square times the power factor, which is cosine theta here, which is 0.833. Sorry, the R1 value. Okay, so we have the current value, and we have the value of R1, which is here 0.641. As we can see here in the question, point R1 is equal to 0.641. Okay, so just substitute here, and the stator losses is 685. Okay, this is in watt. So in this part here, we already find these values. We have the B in, and we have the stator copper loss. So now, since he said here, how about the core loss? He said for the road, the core loss is lumped with the rotational loss. So B core here is already included in the B rotational loss. So there is no B loss here. There is no core loss, because the core loss already included in the rotational loss based on the question. So no need to find core loss. So just we have B in minus B stator, we can find the value of BAG. Okay. So the BAG or the B air gap here is equal to P in minus PSL. So the B in is equal to the value here 12.53 minus 685 equal to, this is the value of the air gap power in one. Okay. Then this value of air gap power, in order to find the value of the converted voltage as required by in the question here, the B converted and B out, we need to find also rotor loss. So B air gap minus the B rotor copper loss, it will give you the value of the B converted. So as you can see here, B converted equal to, either you can say you can calculate, actually you have two options. You can calculate the value of the copper loss by finding I2 current, but since we do not have have the value of the rotor current here, we just go to find or to apply this formula. From this formula here, B air or B converted equal to 1 minus S times B air gap. Okay, so the formula said B converted, this is the required converted, is equal to 1 minus S P air gap. Okay, so we have S here and we have the power air gap, so we can just substitute for S value and the power air gap value. Then we can find, this is the S value, which is 0.02, and this is the P air gap value from the previous one. We can find the P converted. P out here, the output based on the graph here, the flow graph, the P out is equal to B converted minus the mechanical losses. Okay, so since they have B converted and they have the mechanical losses here is given in the question, he said the mechanical losses are 100 1100 watt. This is the mechanical losses, rotational losses or mechanical losses here. So we just substitute for the value here. So it will be B out equal to B converted minus the B mechanical losses, which is 1100. So this one 1585 minus 1180. So it gives you the P out. Okay. This is the B out in watt. If you want to convert it into horsepower, you are going to divide it over 746. So it gives you 14.1. 14.1 is a little, it's like more than half of the total load. Okay, this represents the output or the total load, but this one is just half of the load or less than the half of the output load, rated load. Okay. After that, the third or the fourth requirement or the fifth requirement here is to find the induced torque and the load torque. Okay, the induced torque actually is the torque which be generated in the from the power of the air gap. This is the induced torque. The induced torque will be generated here in this area, while the output torque will be the torque that we are going to take from the machines. Okay. So the induced torque here is depends on the power which is transferred from the stator winding or from the stator to the rotor. Okay, and the formula that we know, the formula or the general formula of the power with respect to the torque, tau is equal to P over omega. Depend on which P, which omega, then the value will be changed. If we are talking about the induced torque, we are going to use the power of air gap and the synchronous speed. Because this power of air gap, the power which transfer from the stator to the rotor, and the synchronous speed is the speed of the stator actually, or the magnetic flux of the stator, which is transferred from stator to the rotor. Okay. So B air gap here already calculated in this part in the previous slide. B air gap is here. This B air gap is 11,845. 11,845. You just substitute for 11,845. divided by 2 pi times 1800. This represents ns actually, omega s or omega synchronous here equal to 2 pi over 60 times ns. Ns is equal to 1800. You just substitute to find the value of induced torque. In order to find the load torque, this P will become P out. So we are going to use the P out, and this omega will become the rotor speed or the machine speed. Okay, so it's become P out over omega m. The P out already here is equal to 10,485, and the machine speed is 1760. We already calculate in the first question here, or in the first part, 1760. Okay, so the value of the P load, I mean the tau load or the torque of the load, will equal to 56.9 Newton meter. Okay, the last part of this example is to find the value of the efficiency. So the efficiency is required to find the P out over P in. The formula for the efficiency is equal to P out over P in. So the P in here is the CH3 I1 V1 we already calculated before, which is equal to 10,485, and the B out is the power that we have here, which is I mean, this is sorry, this is the B out, which is 10,485, the power that we calculated for B out. The B in is the input power that we got from the in the previous slide here. This is the value of P in, which is 12,530. Okay, so you just substitute 10,485 over 12,530 both in 1 times 100. So this will be the value of our efficiency of the induction motor. It's 83.7. Thank you. We're going to continue in the next video.